Inverting amplifier with resistive load. How to find gain of an inverting amplifier? Using three methods. One is general approach, second is the intuitive approach, third is the small signal model approach, and then I will explain how we can increase the gain of an inverting amplifier. Here is the circuit of an inverter with resistive load. It consists of an NMOS and a resistive load R. Input is provided to the gate of the NMOS and output is taken at the drain of the NMOS. So here VGS equals to Vin and the drain to source voltage is Vout or Uout. This circuit acts like an inverter. So when the input voltage, that is Uin, equals to 0, the output voltage should be high, that is UDD. So when Uin equals to 0, the MOSFET is in off, so the output voltage Uout equals to UDD, as drain current ID equals to 0. And when Uin is at UDD, the MOSFET is completely turned on and the output voltage Uout will be equal to 0. So when Uin equals to 0, output voltage is at 1.2 volts, that is UDD, and when Uin is at UDD, the output voltage is 0. So it works like an inverter, and the equation is given by Uout equals to UDD minus ID times R. I will explain the input output characteristics of this circuit. So when Uin is lesser than the threshold voltage, that is UTH, the MOSFET is off, the drain current ID equals to 0, therefore the output voltage will be equal to UDD. When the input voltage, that is UGS, is greater than threshold voltage, the MOSFET starts to conduct, so there will be some drain current, and the output Uout is given by UDD minus ID times R. Here the output voltage, that is Uout, which is equal to UDS, will be greater than UGS minus UTH. So in this region the MOSFET is operating in saturation region, and when UDS is lesser than UGS minus UTH, that is in this region, the MOSFET is operating in triode region. In digital circuits use the off region and the triode region of the MOSFET, whereas in analog design we use the MOSFET in the saturation region, where we get amplification. So generally we bias the circuit by selecting R value and UGS value such that the output voltage is always at UDD by 2. So this is the bias point. For certain UGS 0 and certain value of R, the output voltage will be at UDD by 2, that is 0.6 volts. So by setting the R value and by setting the UGS value, we are setting the ID current. So we can bias or set the output voltage Uout to be at 0.6 volts. And when we apply small signal, that is delta UGS, there will be an output voltage change which is called to delta UDS. So the gain is given by output voltage by input voltage, that equals to delta UDS by delta UGS. Gain of the inverter is given by the output voltage by input voltage, that is change in output voltage, that is delta UDS, because of change in input voltage, that is delta UN. So here, when UGS is reduced by delta UGS, the output voltage UDS is increasing by delta UDS. So when the input voltage is reducing by a small amount, the output voltage is increasing by large amount. So this circuit has a negative gain. Setting the bias point. The bias point is set by the input voltage, that is UGS, and by setting the value of the resistor R. Here the output voltage U out is given by U out equals to UDD minus ID times R. The transfer characteristics of the resistor has to be drawn, that is, when U out equals to 0, find what is ID, that is UDD by R, that is this point, and when ID equals to 0, what is U out? U out will be equal to UDD, that is this point. The line joining these 2 points is the transfer characteristics of the resistor. And when UGS is set to 0.3 volts, UGS is set to 0.3 volts, we have the transfer characteristics line, which is shown in the red. The point where the transfer characteristics of the MOSFET and the resistor coincides is the bias point, BP, shown here. And now when we apply a small change in input voltage, that is UGS, which is shown here, which is equals to UGS, maybe if this is UGS naught, this will be UGS naught plus delta UGS. We get a new transfer characteristics plot of the MOSFET for UGS naught plus delta UGS. So the output voltage will be changed from UDS naught to UDS naught minus delta UDS, and the point of coincidence or intersection between the black line and the MOSFET transfer characteristic line is the new bias point for UGS naught plus delta UGS. The gain is given by delta UDS divided by delta UGS, as shown here. Now, how to find the gain? General method, we know output voltage out equals to UDD minus ID times R. In saturation region, the drain current is given by ID equals to beta by 2 into UGS minus UTH square. Substituting ID in this equation, we get U out equals to UDD minus beta by 2 into U in minus UTH square into R. Dou U out by dou UN is the gain, which equals to, when differentiated, gives minus beta times UN minus UTH times R. We know that beta times UN minus UTH or beta times UGS minus UTH is nothing but the transconductance of the transistor, equals to GM. So gain equals to delta U out by delta UN equals to minus GM1 times R. The second method is the intuitive analysis. So delta UN, that is delta UGS, at the input of the NMOS results in delta ID, which is decided by the transconductance of the transistor, that is GM1, which equals to delta ID by delta UGS. So delta ID equals to GM1 times delta UN. Delta ID results in delta U out or delta UDS, which is decided by the resistor R. From the equation we know that delta UDS equals UDD minus ID times R. Delta UDS by delta ID equals to minus R. So delta UDS equals to minus R times delta ID. So change in output voltage equals to minus R times delta ID, which we obtained from this equation when replaced gives GM1 times delta UN. So gain equals to delta U out by delta UN equals to minus GM1 times R. Third approach to find the gain of the inverting amplifier is the small signal analysis approach. For small signal analysis approach, short all the DC sources, that is short UDD, which is a DC source to ground. Draw the small signal model of the circuit. Small signal model of the inverter circuit. So first we draw the small signal model of the NMOS transistor. Gate, source and bulk are shorted, source comma bulk, then drain. UN equals to UGS, and then the output current is given by GM1 times UGS, and then we have an RDS. Here the resistor is connected between the drain and ground, since UDD is shorted to ground. So we have an R coming into picture. So we know that gain equals to minus GM times R out. We have to find the GM and R out. GM, how to find GM? GM equals to I out divided by UN given U out equals to 0. So when U out equals to 0, we can short drain to source together. So when drain to source is shorted, I out will be equal to GM1 times UGS. So I out by UN equals to GM1. Therefore GM is equals to GM1. Next is finding R out. R out equals to U out by I out given UN equals to 0. So when UN equals to 0, we short gate to source. So this term GM1 times UGS is gone. So we are left with this part. So here U out is nothing but I out times R parallel RDS. So U out by I out equals to R out equals to R parallel RDS. So gain equals to minus GM times R out. So when we replace GM and R out, which we have defined earlier here, so gain equals to minus GM1 times R parallel RDS. So here RDS is the output resistance of the transistor. It will be generally in the range of 10 mega ohms, and R here we have chosen to be 10 kilo ohm. So when we do the parallel value of R parallel to RDS will be equal to R. So gain will be equal to minus GM1 times R. How to increase gain of the inverting amplifier? Gain of the inverting amplifier is given by gain equals to minus GM times R. We can increase GM to increase gain, or we have to increase R, that is the load resistance. What is the effect of increasing R on the bias point? Here we can see that as R increases, the point here reduces or comes down to this new point UDD by R dash, because as R increases, UDD by R reduces. And when we bias the MOS transistor to VGS naught, which equals to 0.3 volts, the bias point, the new bias point is at this location, and this location is in the linear region of the MOS transistor, which is not good. We want the bias point to be in the saturation region for amplification. Hence, by increasing the load resistance R, we are bringing the transistor to linear region. Hence, for setting the bias point or large signal analysis, we need R to be low, and for increasing the gain, we need R to be high. So we need large signal resistance of the load to be low and small signal resistance of the load to be high. How do we get this? This can be obtained by using a constant current source as load. This is the symbol of constant current source. This provides constant current irrespective of the voltage across it, and when operated at this point, the large signal resistance is given by V naught by I naught, and the small signal resistance of the constant current source is infinity, because we can see here that the slope is 0, therefore G equals to delta I by delta V equals to 0, and hence R, that is the small signal resistance of the constant current source, equals to infinity. Constant current source can be generated by using an NMOS device whose gate to source is fixed. So when we fix the gate to source voltage and when we operate the NMOS device in saturation region, it acts like a constant current source as seen here. So the current is constant when operated in the saturation region and when VGS is fixed. The large signal resistance when operated at this point is given by VDS naught by ID naught, and the small signal resistance is nothing but 1 by GDS. Here the slope of this line is 0, so GDS is 0 and RDS is infinite. So we have a very high small signal resistance and a low large signal resistance. Hence, by using a constant current source as load, the gain of the inverting amplifier can be increased. And now the gain equals to minus GM times RDS, where RDS will be in the range of several mega ohms. With constant current source as load as shown here, R out will be of this circuit will be RDS1 parallel with infinity, that is constant current sources will be open for small signal analysis. So gain of this circuit equals to minus GM1 times RDS1. So the gain is very high. When ideal constant current source is replaced by a pmos constant current source, that is whose gate to source voltage is fixed. Here the gate is fixed to VB. Then the pmos can, and when the pmos is operated in saturation region, the pmos can act like a constant current source. So in this case, R out will be RDS1 parallel to RDS2, which I will show in the small signal model analysis. So in the small signal model, short all the constant sources, that is VB is shorted to ground, V and the VDD is shorted to ground as shown here. Draw the small signal model. G1 S1, VGS1 is V in. So we have GM1 V in, RDS1, VGS2 equals to 0. Therefore, GM2 VGS2 term is not here. RDS2 is connected between V out and ground, shown here. To find R out, make V in equals to 0. So when V in is shorted, GM1 times V in terms goes away. Therefore, now R out will be equal to RDS1 parallel RDS2. To find GM, make V out equals to 0. So when V out is shorted, the current I out will be equal to GM1 times V in. Therefore, I out by V in equals to GM1. Therefore, GM equals to GM1. So gain of this circuit is minus GM1 times RDS1 parallel RDS2.